Okay, so last week we just proved this theorem, so I wanted to reintroduce it. Let Rn have the standard topology with the standard metric D. Then the set A is a subset of Rn. A subset of Rn, is compact if and only if it's closed and bounded. You remember that?
Yeah.
Do you remember each of those three words? Closed, bounded, and compact?
Well, can we go over bounded again?
Bounded. A set is bounded if all the points are within some distance of each other. So notice that you can only talk about bounded if you have a metric.
A metric.
So a metric gives you the distance between 2 points. A set is bounded if all the points are within some distance of each other. It never takes off to infinity. So in R2, that set's bounded. Whereas a line that goes off like that is not bounded.
Mm-hmm.
Okay? That's bounded. Hopefully you remember what closed is. What's closed?
The
intersection of closed sets.
No, that's
you
a
can't
property
define
of
a closed set
Yeah,
as an intersection of closed sets.
It's the word for it, something, it's like its opposite is an open set.
Perfect. It's the complement of an open set.
Yeah.
When is a set closed? When its complement is open. You were probably thinking about the three topological properties we proved for closed sets. We proved that the empty set and the whole set are always closed, that a finite or that an infinite intersection of closed sets is closed, and a finite union of closed sets is closed.
Can we go over the definition of a compact?
Yeah, so now compact. What did it mean for a set to be compact? Told you this is the weirdest definition that we'll cover in topology.
It had the cover, which had finite
What's a
subcovers.
cover?
A cover,
Is a set that covers another set.
It's a collection of sets.
yeah.
Yeah, a collection of sets that cover your given set. Right? What's an open cover?
A collection of open sets.
Yeah, a cover that's composed of open sets. All right, now what was compact?
Compact is it had like subcovers.
It has
It has a finite number of subcovers.
Almost. You're getting the right words.
a finite number of sub.
Every open cover has a finite subcover.
Yeah.
Subcover, not covers. Well, it can have subcovers, right?
If it has one, then you're done. It could have many. If it has one, then you're done.
Okay.
Right? If I say there exists an even number, could be infinitely many, but there exists means at least one. For every open cover, there exists a finite subcover. Maybe infinitely many, but there's at least one. Okay. So that was theorem 7.15. This was the last thing we proved. And I told you next we were going to do a bunch of examples now to talk about some sets that we've been working with that we know and love and talk about whether or not they're compact. So let's look at S1 as a subset of R2. Do you remember what S1 is?
Is it just a circle?
Just a circle. Yeah, just the border of the circle. Not inside, not outside, just the actual line I drew. Just those points.
Right.
Is that set compact?
Yeah, I would think so.
How do you know?
Because I picture sets, open sets around it.
That's way too hard. The whole point of the Serum is like you don't have to think about it that way.
Because
Because it's
it's closed and bounded.
closed and bounded. That's real easy to think about. Is it closed? Yes. Does it take off to infinity?
No.
Okay, it's closed and bounded. Alright, next, let's look at the torus. The torus T, it's compact. We're going to give three different arguments for this real quick. First off, one way that we can create the torus is S1, a circle in the xy plane, rotated around the y-axis is what I meant that to say. So here's my x-axis, here's my y-axis. One way that we can think about the torus is, if I take this circle and I rotate it around the y-axis, so it comes out of the board and it goes back in and comes around. So it's rotating around the y-axis. You see what I'm saying?
Can we get a picture of it again?
Oh, what a torus
Oh,
actually
it's a
looks like,
donut.
surface of a donut. Yeah,
Okay.
okay, surface of a donut. So if you take the circle and you rotate it around the y-axis. So it comes out in the z direction, three-dimensional. Comes out and then goes back into the whiteboard, so it's going around, so it goes back into the whiteboard over here. And it wraps around. You see what I'm saying?
Mm-hmm.
So, you can think about it as a circle in the xy plane, rotate around the y-axis. That would be a closed and bounded set, right?
Yeah.
That's the most straightforward way that we think about the torus. Another way that we define the torus is S1 cross S1. One of the things we proved last time is that a compact set crossed with a compact set is still a compact set.
Yep.
Since we know S1 is compact, then we know that that cross product is compact.
Yes.
Right?
Okay.
Another way, hopefully you remember drawing these squares and then identifying sides. So grab a piece of paper real quick so we can remember what this is again. So if I identify this side with this side, that takes my paper and makes it like this. And then if I identify the top with the bottom,
Yep.
that gives me a torus, right? Now notice, is this square, just a square in R2, forget the arrows for a second, is the square a compact set? Now we're including the points inside. That square is compact, right? It's closed, it's bounded, it's compact. Now, when we do this gluing, then we are using a, you remember what it's called? We're creating a quotient space. We're using a quotient map. You remember talking about quotient spaces?
Yeah.
That's when you glue the points together.
Yeah.
The point is that those quotient maps are continuous functions. So when we glue, so when I start with this square and then I glue those sides together, when I start with the square and I glue these sides together, and I glue the top with the bottom, that's a continuous function that we ran this through. I take my square, I run it through the function, and it spits out the torus. That function is continuous. We proved that continuous functions preserve compactness.
Yeah.
So, since every quotient map is continuous, then every quotient map we did to this square produces a compact space. So my torus is compact.
Mm-hmm.
Similarly, my annulus is compact. The annulus is we take this and we hook it with this. Why is it called annulus? Well, if I stretch it out, it's going to look like a washer. If I were to pull this paper and flatten it out, remember, you can stretch and that doesn't change anything.
Yeah.
I can flatten that out and make it look like a little washer, right?
A washer?
Washer as in like with a screw, you have a washer around your screw that you're putting in, a bolt. If you put furniture together, then you've dealt with washers 100 times. Have you ever assembled a piece of furniture?
Yes, but I don't read what it's called.
That's called a washer. That ring,
Oh, okay.
that flat ring looking thing, yeah, that's what you mean by a washer. So, that's the annulus, which, here it is. You remember what this thing is?
The Mobius band.
The Mobius band. Wonderful. Is the Mobius band compact?
Yeah.
Yeah! We're applying a continuous function to a compact domain. The Klein bottle. You remember the Klein bottle?
Mm-hmm.
Yeah.
Is that thing compact?
Yeah.
Yeah, I get it from a quotient space with this.
Mhm.
What about the sphere?
Mhm.
Yeah, I can get it from a quotient space from this. And the projective plane. Right? You probably don't remember the projective plane. That's okay. But the point is, those typical topological spaces that kept coming up over and over again, that we kept using by messing with these squares, every single one of them compact.
So what's an example of a non-compact set that we would be familiar with?
Y equals 3 in R2.
Okay.
Right, just a constant function. Whoop. It's not compact. Good?
Mm-hmm.
Okay. So, Theorem 7.16. Let X be a metric space, and let A be compact in X. So A is a subset of X, and it's a compact subset of X. With me so far? we don't have Emma here, and none of you have done calculus. Oh, James did calculus. So this might be a little bit of a throwback for him. The sequential compactness theorem. Here it is in topology. If xn is a sequence in A, then there exists a subsequence of xn such that it converges to a point in A. Did I lose you in that language?
I think I got it. Can we?
Let's say it one more time.
Yeah.
Do you remember what a sequence is?
Yeah,
What?
it's just a set of numbers.
It's not just a set. How big is a sequence?
Infinite.
It's always infinite. So a sequence is a function whose domain is all the positive integers. 1 goes to something, 2 goes to something, 3 goes to something, 4 goes to something, etc. And we typically use x of 1 to signify what the first thing goes to, comma, x of 2, that's what 2 goes to, comma, dot, 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 and in general, x of n is what n goes to, dot, 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 and we keep writing it. The common sequence that we've used over and over again in this class is 1 over n. That's shorthand for 1 over 1, 1 over 2, 1 over 3, 1 over 4, etc.
Mm-hmm.
So xn is, this is just a generic I just realized, in this class we're used to using parentheses xn, huh? Not curly braces. Sorry, in calculus we always use curly braces, and so I accidentally use curly braces. Does it matter to you which way I do it?
No, not at all.
Okay, so we'll stick with what I have written. Okay, so if xn is a sequence in A, so whatever A looks like, so A might be some set like this, and then we have a sequence in there. Who knows what it does? But some sequence in there. Infinitely many points, all inside of A. You with me so far?
Mm-hmm.
So xn is a sequence in A. We're saying if A is compact, then there has to be some little a in here, some point in there, such that a subsequence of xn converges to A, gets closer and closer and closer to that little a. What's a subsequence of a sequence? A subsequence, if we're looking at 1 over n, would be something like 1 over 2, 1 over 5, 1 over 9, and we keep on going, picking terms out of our sequence, of our initial sequence. We still have to pick infinitely many.
Mm-hmm.
But it's not all.
It could be all of them. It's still a subsequence if you use all of them. So every sequence is a subsequence of itself, the way that every set is a subset of itself. But you could also eliminate some terms, a finite number of terms. Well, you can also eliminate infinitely many. There just has to be infinitely many left when you're done. One of those weird things where if you subtract infinity from infinity, you could still have infinity. Right? Take all the positive integers, now get rid of all the even ones. How many numbers do you have? Right? So it's that type of thinking. So you could view all the positive integers in order as a sequence. Now get rid of all the evens. Now you have a subsequence.
Okay.
Second condition of a subsequence, it still has to be in the same order as the sequence. So I couldn't have 1/2, 1/5, 1/9, and then come right here and write 1/2, or you can't have repeating terms, but I also couldn't put 1/3 there. Once I get to 1/5, I can't go back and pick older terms. I can only pick terms after 1/5, and then after 1/9, etc. Subsequence. Is this ringing bells? Are you remembering when we talked about this?
Yeah.
Okay, so that's what we mean by a subsequence. Our generic notation for a subsequence is this. If this is a sequence, this is a subsequence. Where n sub m is referencing that little n there. So instead of having the sequence x sub 1, x sub 2, x sub 3, x sub 4, we might instead just have x sub 2, x sub 4. And so you can think about this 2, 4, the subscripts here, you can think about them as a sequence, and that sequence would be n sub m. And then you're using that subsequence, 2, 4, whatever, to pick the terms out of here that you want to use. That's where that notation comes from.
Okay.
So common notation just for referencing some subsequence. So if this is your sequence, then that's typically how we say, and for some subsequence, that's the notation. So let's say this one more time and see if you still have any questions about what it's saying. If xn is a sequence in big A, then there exists a subsequence such that it converges to a point in big A. Do you understand what we're trying to prove?
Yeah.
Now, convergence in this class, you might not remember what that meant. A sequence converges to a point. So I've got some sequence. Let's pick an actual example of one and what we know it converges to. So let's look at the sequence 1 over n. What does that converge to?
0.
It converges to 0. So our topological definition of it converging to 0 is for any open set you pick containing 0, for any teeny tiny ball you pick surrounding 0, it will contain all the terms in this sequence from some point onwards. So it might not contain the first point, it might not contain the second, it might not contain the third, or the fourth, or the fifth, or the sixth, or the seventh, but it's going to eventually contain a point, and all the points after that. Does that make sense?
Mm-hmm.
That's what it meant to converge. So a sequence converges to a point if, for any open ball you pick around that point, it contains every term in the sequence from some index onwards. So it might not contain the first 10 trillion, but it contains all of them after that, so it still contains infinitely many. Make sense? And notice, hopefully that appeals to your intuition. No matter how small of an interval I pick around 0, it's always going to contain infinitely many elements from this set. Does that appeal to your intuition?
Mm-hmm.
Wonderful. Okay. So that's what we're going to prove here. So first we're going to show that there exists a little a in big A, such that every open ball centered at A contains infinitely many elements of xn. So first I'm going to show that I can find an open ball around my A such that it contains infinitely many terms from our sequence. And then I'm going to prove that, and that sequence has a subsequence which converges to it. So we're going to break this up in pieces. You with me?
Yeah.
Okay, so first I'm going to show that there is some little a in big A such that every open ball centered at little a contains infinitely many terms in this sequence. I'm going to do this proof by contradiction. So assume by way of contradiction that for any little a in big A you pick, there exists some open ball around that point that only contains finitely many elements of our sequence. So for every single a, little a and big A, there is some open ball you can find around that point such that it only contains finitely many elements from this sequence. And we're going to get a contradiction using the fact that big A is compact. So then O equal to the set of all those open balls. We have an open ball around each of them for all little a and big A is going to be an open cover. Does that make sense? Because we used all of A. So all these open balls are definitely going to cover big A. Right? Okay, so here's an open cover. We know that A is compact, which means that O has a finite subcover. So then there exists some O prime, or finite subcover, equal to the ball centered at A1, comma, the ball centered at A2, comma, dot, 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 the ball centered at AN. So in other words, we can pick just n of these open balls, and it will cover all of A. You with me? Now, what do we know about each of these open balls? They only contain finitely many elements in Xn. Right?
Yeah, in your sequence.
Yeah. So each of these open balls only contains finitely many terms in this sequence. Right?
Mm-hmm.
How many terms are in this sequence?
Infinite.
Infinite. How many open balls do I have?
Finite.
Finite. How many terms in the sequence are in each of these open balls?
Finite.
Finite. Is this whole sequence in A?
Yes.
Does this contain all of A?
Yes.
There's going to be our contradiction. You see our logic for how this is going to flow? So now we'll just say it again, but I figure doing it twice might help. So then O prime is finite. and each ball in O' only contains finitely many elements of Xn. Since all of Xn is in A, then Xn is finite. Contradiction. Because Xn is infinite, it's a sequence. Okay, so I think you all understood how that led to contradiction. Right? So what did we contradict? Well, so then what can we conclude? So then we can conclude that there must be some A, some little a and big A, such that every open ball centered at that little a contains infinitely many terms of our sequence.
Which means that it converges, right?
Our sequence doesn't necessarily converge. It's going to have a subsequence that converges.
That's right.
Because let me give you an example of a sequence that doesn't converge. So let's pretend that A is equal to the interval 0, 1, which is definitely compact, right?
Mm-hmm.
And let's say that our sequence, I'll call it S, I guess, is equal to 1, 0, 1, 0, 1, 0,
That can be
repeating
sequence.
forever. What does that converge to? Is it getting closer and closer to 1, or is it getting closer and closer to 0? No. It's not getting closer and closer to anything. But notice, what's a subsequence of this?
1, 2, 0.
1, 1, 1, 1, 1. That's a subsequence. What does that converge to?
1.
Is 1 in there?
Yeah.
Yeah, that's what we're saying. We're saying it doesn't matter how you pick the sequence. As long as you keep it in there, then I can find a subsequence of that sequence that converges to a point in there. That make sense?
Mm-hmm.
So, we already showed that there must exist some little a and big A, such that every open ball centered at little a contains infinitely many elements of Xn. So, let's see where we say that down here. Therefore, there exists little a and big A, such that every open ball around little a contains infinitely many elements of X of n. So then we're going to jump. I don't know if that's still on my camera. It is, but we'll just move the camera while I'm here anyways. To that, put these back under so it's not so shaky. Which actually looked like it worked a lot better. Yeah, you didn't notice that when you went back and watched it? For your last lecture?
Nope.
You must need glasses or something.
Yeah, dude. What about
Okay. So we know that there is some little a and big A, such that every possible open ball you can construct around it contains infinitely many terms from Xn. From our sequence. Right?
Mm-hmm.
Okay. So now I am going to construct a subsequence from our given sequence such that it converges to little a. Then, for every positive integer, because I'm creating now a subsequence, so I need a subsequence is still a sequence, so I need to map every positive integer to something. So then, for every positive integer, let x sub n sub m be the point in the open ball centered at a with radius 1 over n. So in other words, there has to be a point in Xn, there has to be a point in our sequence that's in the open ball centered at a with radius 1, right?
Mm-hmm.
Okay, pick that point. Now, there has to be a point later in the sequence, since there's infinitely many, there has to be a point later in the sequence that's in the ball centered at a with radius 1/2.
Yeah.
And then there has to be one when you lower the radius to 1/3, and 1/4, and 1/5, and 1/6, and 1/7, and 1/8, and 1/9, and 1/10, etc. So, you can see how how each term that we pick is getting closer and closer to A. Right?
Yeah.
Okay. So, then there exists, then for all little m for every positive integer, there exists an open ball with radius 1 over m containing a term in our sequence that came after the previous term. So we're saying pick them in order. There's infinitely many to choose from. So we're saying just don't pick one that's prior to a point you've already used. Don't accidentally go from 1/5 to 1/4, even if 1/4 still happens to work. Make sure you pick something after 1/5. How am I guaranteed I can do that? There's infinitely many, and I've only used a finite number.
I see.
So if I get rid of those finite numbers inside the open ball, there's still infinitely many to choose from. So do you see how we always have a choice that satisfies this, where we picked one later in the sequence? This is not saying x sub n is less than x sub n sub n. Notice that these are not the x's. We're talking about the subscripts here. The subscript of the next one has to be bigger than the subscript of the previous one. So it has, if you use x sub 5, then you can't use x sub 4 now. You have to use x sub 6 or later. That's what that's saying. Does that make sense? Okay. So then, this is a subsequence of xn, and it converges to A.
Okay. I see how we did it, but why in topology do we care?
Why in topology do we care? In calculus, so notice that this whole section was basically talking about topology when we're talking about metric spaces, and particularly when we're talking about metric spaces using the Euclidean metric in the real numbers. So we're limiting our scope in topology now to talking about particular sets that we're interested in. This is very calculus related, and this is something that we use in calculus all the time. How many times do we use sequences in calculus, James?
Every time we have done with the limit.
Every time you're talking about a limit, you're really talking about a sequence somehow. So the four major ideas that you talk about in calculus are limits, continuity, derivatives, and integrals. A limit is obviously a limit. Continuity has to do with a limit giving a specific value, so you're still talking about limits. A derivative is just a limit, and an integral is just a limit. So you're always talking about limits, which somewhere behind the scenes is referencing some sequence of numbers approaching a particular number.
So because I haven't really gotten into that type of stuff, then
Yeah, you haven't come across the applications of this, but the counterpart name to this theorem in calculus is called the sequential compactness theorem. And it's one that is one of your big theorems that you cover in calculus when you're going through it.
Cover it really early.
Yes, you have to, because remember how you define continuity. Continuity in calculus is if a sequence converges to x, then the image of the sequence converges to the image of x. That's how we define continuous functions. And you can see how that's using limits.
yeah.
Yeah. Okay. So that covers that. Now we're jumping to our last section, the extreme value theorem. The extreme value theorem is a very intuitive theorem. You're almost going to ask, why do we even have to prove that? It's so intuitive. But let's go over what it is in calculus. In calculus, the extreme value theorem is, let f be a function from the closed interval ab to r such that f is continuous. Then f achieves a max and a min on that closed interval. Not a, b, but a max and a min. So here's my a, here's my b, that's my domain. Here's my function, plotting the points, right? Here's where it achieves the minimum, here's where it achieves the max. Another example, here's my domain a, b, here's my function. Now it happens to achieve a minimum at little a and a max at big B, but that wasn't necessarily the case. Notice that we include the endpoints, so that and that are points.
Okay.
Now, there doesn't have to be just one place where it achieves a max and one place where it achieves a min. We're saying that there is at least a point where it achieves a max and at least a point where it achieves a min. Right? Because I could have had this function, instead of it like that, I could have drawn something that went like this. Down, up, down, up, down, up, down, and out. Something like that. And those were all meant to be the same height. So that, and that are all the same height, and this, and this, that was terrible, are all the same low. So it can happen in multiple places, but we're guaranteed that somewhere along the way it achieves a max and achieves a min. And then finally, here's another weird case where we have a constant function. So this is like f of x equals 3. What's the min? 3. What's the max? 3. Where does it achieve the minimum? Anywhere in the interval. Where does it achieve the max? Anywhere in the interval. Good?
Yeah.
We haven't proved anything yet. This is just intuition for what the theorem gives us.
But you said it should be pretty intuitive. Like,
You've got, so here's the way to make it appeal to your intuition. I say, Peter, you've got to start by drawing a point somewhere on this line, and you've got to end drawing a point on this line. So you have to start somewhere on here, pick where to put your pencil, and now you have to draw it to somewhere over here without picking up your pencil. Do it however you want, and you can't backtrack, it has to be a function, so I can't draw under it once I've drawn. I have to keep moving to the right as I draw. No matter how I draw that, whatever my picture looks like, it's going to have reached a minimum value, and it's going to have reached a maximum value.
okay.
That's what it says. Maybe that's not stupid intuitive, like I thought. Alright. But that's the extreme value theorem. And extreme values because it achieves extreme values, a min and a max. That's where it gets its name. Okay, so that's what we're going to prove, but we're going to prove it topologically. We're going to prove a more general one, and then we'll see how this obviously follows from the general one we proved. How are we going to change it? Instead of requiring this to be a closed bounded interval in the real numbers, we're going to replace that with any compact topological space, and it's still going to be true. So obviously this is a compact topological space. When you view it as a subset of R, we can replace it with any compact topological space, and it still holds, is what we're going to show.
That in your compact space, if you put a function through it, then it has
Any
a
continuous function
okay.
from a compact space to R achieves a maximum and a minimum.
To R.
Yeah, it has to be to R, we can't change this.
Okay.
The counterpart to this, you might remember the intermediate value theorem. The intermediate value theorem was that if a function achieves two values, then it achieves a value somewhere in the middle of them. And the intermediate value theorem held for when the domain was connected.
I feel like we did go through it.
We did go through it, and you remember we had an instant corollary talking about how it showed that there's always two places on the Earth with the exact same temperature on opposite sides of the Earth. Yeah.
There it is.
Yeah.
It was
And it's
pretty-
real easy to prove.
That's interesting.
Yeah. There's two places on opposite sides of the Earth with the exact same temperature. There's two places on opposite sides of the Earth with the exact same humidity. There's two places on opposite sides of the Earth with the exact same elevation.
That makes sense.
It does. Now, there's two places on opposite sides of the Earth with the exact same temperature. Why should there be?
I mean, as you have a,
Why can't one side always just be hot and the other side always just be cold?
because of the rotation.
What, the Earth didn't rotate? It has nothing to do with the fact that the Earth's rotating.
Oh, it doesn't?
Yeah.
Nope.
The Earth
It has to.
is, yeah.
It only has to do with the fact that you can roughly approximate the Earth with a sphere, and a sphere is a
Connected space.
connected topological space.
Interesting.
So it just has to do with the fact that a sphere is a connected topological space. Temperature is a continuous function. There you go. We're done. Intermediate value theorem. Well, we used a version of Rolle's theorem, but I don't know if we use that name. You can go rewatch it. It's really not that hard. What were we saying? Oh, extreme value theorem. Okay, so extreme value theorem. Here's what is in calculus. Now we're going to do a quick lemma, then we're going to prove the extreme value theorem, and then note some stuff. So, what's the lemma that we're going to prove? Let A be any subset of R that's compact. Then there exist 2 points in A such that one of them's a minimum and one of them's a maximum. So A contains its minimum point and its maximum point if it is a compact subset of R. Now hopefully this already appeals to our intuition. We already know if it's a compact subset of R, then what does it look like?
It's closed and bounded.
Closed and bounded.
Yep.
So it has to look like unions of these things. Right? And all we're proving is that somewhere inside this set it contains its minimum, in this case it's right here, and somewhere in this set it contains its maximum, in this case it's right here. Now notice not every set contains a minimum and a maximum. For example, consider the open interval like this, where this is 1 and this is 2. Or writing it another way, the open interval 1 to 2.
Yeah.
That contains no max and no min. So this isn't something that you automatically get for free, but it turns out if A is compact, and it's a subset of the real numbers, if it's a compact subset of the real numbers, then you do get this for free. And that's what we're going to show real quick.
Okay.
But hopefully it makes intuitive sense, right? Because we're always talking about just a union of closed intervals. Just take the rightmost closed interval and take its right-hand point, and take the left-hand most closed interval, take its left-hand point. That's your little m and big M. Okay, so let's prove it. So since A is bounded, then it is closed and, sorry.
If A is
A is compact, then it's closed and bounded.
Since A is compact, then we know it's bounded, right? And then since A is bounded, sorry, I skipped a step here, my brain jumped. And then since A is bounded, what does that mean? Then there must exist some big M. Did we talk about least upper? We did. We talked about least upper bound.
Yeah, we did.
Least upper bound, supremum, same thing. That's what sub of A means. The supremum of A, the least upper bound of A. If A is a bounded set, then that means that it's bounded from above for sure, right?
I'm sorry. Can we go over least upper bound again?
Well, yeah, I'm going over bounded and we'll reintroduce least upper bound. So bounded. What does it mean for a set to be bounded? Bounded from above. We'll just talk about from above. If my set is bounded from above, then that means I can find a really big number bigger than everything in my set. So we got this set over here, all the numbers from 1 to 2, not including 1 and 2. It's bounded from above by 200. It's also bounded from above by 99. It's also bounded above by 3. It's also bounded from above by 2.5. Now, one of our axioms on the real numbers is that every set of numbers bounded from above has a least upper bound, has a smallest upper bound, or a supremum. Least upper bound or supremum. So, when we look at this set, what is its least upper bound?
2.
2. Exactly. So, since A is bounded, then, where are we? Since A is bounded, then there must exist some big M equal to its supremum. It must have some least upper bound, call it big M. Okay? So it is bounded from above by big M. Now I need to show that big M is actually in the set A, and then we're done.
What are you trying to prove again?
Right. So I'm trying to prove that there exists some big M in A such that M, big M, is greater than or equal to everything in A. Notice that is not the case here. You cannot find an element in here that's greater than or equal to every other element in there.
Yeah.
Right? So it does not hold here. But if you look at this set, I can find an element in there that's greater than or equal to everything in there, namely whatever this point is.
Okay.
You see that? That's what we're proving. So I know that whatever my set looks like, I don't know if my set looks like this or if it looks like this. Whatever my set looks like, I know it's bounded from above, so it has a least upper bound. The least upper bound of this set is 2. The least upper bound of this set is this point right here. Now, if I can just prove that my least upper bound is in the set, then we're done. So notice that this one's not compact because it doesn't contain its least upper bound.
That's right.
I'm going to show that this one, since it is compact, it does contain its least upper bound. That's what we're proving. That make sense? Okay. So, let M equal the supremum of the set. So M is an upper bound. I need to show that M is inside the set now. And then we're done. Because if big M is in the set, then there exists some big M such that this is true. That make sense?
And I guess if you prove it for big M, then it...
Yeah, we're only going to prove for big M, little m, it's identical. You just use the infimum instead of the supremum. But it's the exact same proof. So yeah, sorry, I should have specified that at the beginning that we're just going to be proving this for big M. Okay, and we're going to do it proof by way of contradiction. Assume by way of contradiction that big M is not in A. Now, what do we know about A?
It's compact, so...
It's compact, so it's bounded and it's also closed. Right? So, what's the closure of A?
It's least upper bound.
No, the closure. Do you remember the closure?
Yeah, it's with the line above it.
It's the intersection of all closed sets containing it.
That's
So the closure of A is the intersection of all closed sets containing A.
Yes.
Since A is already closed, it's its own closure.
Mm-hmm. That's right.
A set is closed if and only if it's equal to its closure. That's a proof that we've already done. So another one, a proof that I told you need to memorize it because we use it forward and backwards, left and right, all throughout this class, is that a point is in the closure if and only if every open set around a point intersects the set.
Right.
Or a point is not in the closure if and only if every open ball, or if and only if there exists some open ball around the point that doesn't intersect the set.
Yeah.
So A is its own closure. Since M is not in A, then there must exist some open ball around M that doesn't intersect A.
Yeah.
That make sense?
Mm-hmm.
So A is from here to here. If M is not inside the set, so M somewhere out here, then there must be some really teeny open ball I can put around M without capturing any of A. A is right here. You with me?
Yeah.
That's what we're saying. Open ball, and we're saying epsilon is obviously the radius of that open ball. So assume by way of contradiction that M is not in A, then there must exist some open ball containing M that doesn't intersect A. Right?
Mm-hmm.
Now, if there's an open ball around M that doesn't intersect A, then notice a point to the left of M inside of there is also an upper bound for A. So then, M minus epsilon halves, which is a point to the left but still inside that open ball, is an upper bound for A. Contradiction. Big M was the least upper bound. Big M minus epsilon halves is smaller than big M, and it's an upper bound. Contradiction.
Yeah, I see that.
Good?
That is calculus right there.
Yeah, this whole section is just calculus.
I mean, that'll sum up a lot of your homework problems right there.
It's just calculus in a more generic way.
Yeah.
Actually, this one's completely calculus. We proved this exact same thing in calculus.
Well.
Okay. Therefore, M is in A. This was a proof by contradiction. We said assume by way of contradiction that M is not in A. Contradiction, therefore M is in A. Okay? And then the proof for showing that little m is in A is identical. You just use the infimum and then you add a little bit. You're going to do little m plus epsilon halves for the little ball. Make sense?
Yeah.
How you would do it for little m? Yeah? Okay. So there's our lemma. Now we are ready for the extreme value theorem. Our last major theorem of the class. Okay, so let,
So it's not very long.
no, it's a teeny theorem, really easy to prove. Let big X be compact, and let f from big X to R be continuous. Then, there exist 2 points in big X such that the image of those 2 points are a maximum and a minimum. So notice that we're not using big A and little a the same way that we did in this picture. So I don't know what my start and end points are. All I'm saying is that there exists a little a. Let's see, did I do little a for my min or my max? There exists a little a, namely right here, and a little b, namely right here, such that f of little a gives me the minimum, and f of little b gives me the maximum. There exist 2 points in the domain, call them little a and little b, such that f of little a gives me little m, and f of little b gives me big M.
Okay.
Or in other words, it achieves a max and a min. Understand how this is still saying the exact same thing as this, except for our domain's a little bit different? Let's really quick make the connection how proving this gives us this for free, and then we'll prove it. How does this give me this for free? This is a compact topological space. Let X be compact and let F be a continuous function from a compact topological space to R. This is a compact topological space, so this is just a special case of this. You see how it's just a special case?
Yeah.
How we get this one for free if we got this? Okay, so now let's prove this. That was a good bounce.
Track bounced away from you now.
Huh?
Said your track is now bouncing away from you.
It tried to get back to me. I accidentally dropped it, and it worked so hard to get back into my hand, it just didn't quite bounce high enough. And so I decided, okay, I'll pick you up instead of going to get it anywhere.
Yeah.
For all that effort, you know? So, since f is continuous, since x, I think is what I meant to put here, since x is compact and f is continuous, then f of x is compact. Is a compact subset of R.
Yes.
How do I know that?
Because continuous functions preserve compactness.
Perfect. Continuous functions preserve compactness.
Yeah.
Wonderful. Now, since this is a function from x to r, then f of x is all of r, right?
Yes.
No! This could be the function f of x is equal to 2. Just constant function. Map everything to 2.
Oh.
Okay. So this is not a one-to-one or on-to function, necessarily. It's just continuous. Alright, so let x be compact and let f from x to r be continuous. Then there exists a, b, and x such that f of a is less than or equal to f of x is less than or equal to f of b for all little x in big X. Oh, that was stating it. We were doing this one. Sorry. Since big X is compact and little f is continuous, then f of x is a compact subset of R. Possibly all of R, but for sure, a compact subset of R. With me?
Yeah.
Now, what did our lemma over here just say? Our lemma over here said that if we have some compact subset of R, then there exists a maximum and a minimum in there. Okay? So over here, we know that the image of our function is a compact subset of R. So this set, f of big X, whatever that set is, we know contains a minimum and a maximum. So then, f of x, compact subset of R, contains a max big M and a min little m. You with me on how we got that?
Yeah.
Okay. So, since big M and little m are in the image of big X, then that means that there must have been at least 2 points that map to them.
Yes.
There could have been 10,000 points that map to them, but there's at least 2 points in there that map to them. Right? We don't know how this thing's one-to-one. It's just a continuous function, but it is a function. So I have to map all of x to these points, but yeah, since these 2 points are in the image of big X, then there must have been 2 elements in big X that map to them.
Right.
Does that make sense?
Mm-hmm.
Any questions with that?
No.
Perfect. Then we're done. So then little m is equal to f of a is less than or equal to f of x is less than or equal to f of b is equal to big M for all x in X. The image of every point had to be between little m and big M, which is what f of a and f of b are.
Yep.
So they have to be between f of a and f of b. Follow that?
Mm-hmm.
Yeah.
Wonderful. Compare calc. We already talked about the calc version. Okay. Just didn't want to forget to do that. So, quick corollary. Oh, I see. Let me tell you what the corollary is over here first, and then we'll go back and read it. And it's just a corollary for calculus. So notice over here that when our function is on a closed bounded interval from a to b, then the image of our function is also a closed bounded interval from little m to big M. You see that?
Yes.
Yeah, it would make sense because compactness preserves that, right?
Compactness tells me that there's a min and a max, but notice that we also have every point in between.
Isn't it a continuous function that preserves that?
Yes, continuous.
It's not the compactness that preserves it.
It's the continuous function.
The fact that it's continuous and on a compact domain means it achieves a minimum and a maximum. The fact that it's continuous and on a connected domain means that the image is an interval.
Okay.
So put those together. The image is an interval that contains a minimum and a maximum. The only type of interval that contains its minimum and its maximum is a closed interval.
Yeah.
Does that make sense?
Yeah.
Mm-hmm.
So that's what we're proving in this special case. It's very useful in calculus to know that if your domain's a closed bounded interval and your function's continuous, then your image is also a closed bounded interval. And it's using the extreme value theorem and the intermediate value theorem together. Do you remember exactly what the intermediate value theorem said? It said if your function achieves a value, two values, then it achieves every value in between those two values as well. That's what the intermediate value theorem says. It says if you got a continuous function on a connected domain and it spits out A and it spits out B, then it also spits out every number between A and B. Or if it spits out little m and it spits out big M, then it also spits out every number between little m and big M.
Because if it didn't, it wouldn't be continuous or not or connected.
Yeah.
Right, if it didn't, then you can see how the image now is no longer connected.
Yeah.
And connectedness is preserved by continuity. Yeah, so you're rethinking through how you improve that. Right. Wonderful. Great intuition. Okay, so that's what we're doing here. We're proving that if your domain is a closed bounded interval, then your image is also going to be a closed bounded interval using intermediate value theorem and extreme value theorem. Make sense what we're doing? Because, yeah, I think if you understand the picture, then understanding the proof, straightforward. And obviously it's team proof. So, since f is continuous, then the image of the interval is closed and bounded. Is a closed and bounded set. Right? This is compact, so the image is compact, which means closed and bounded.
Yes.
Right.
Okay.
So I know it's closed and bounded, so it could look like this. It could be this scene with this scene with this scene. It remains to show that it's also an interval and we're done.
Mm-hmm.
So I know it's closed and bounded, but right now I don't know that it doesn't look like this. I'm trying to say, no, it can only look like this. It can't possibly have gaps. Because this is still a closed bounded interval, or a closed bounded set. These three union together. I still need to argue it looks like this. So I know it at least looks like something like this. I still need to argue, no, it actually looks like this. It's just one interval. It's not multiple intervals. You understand what we still need to show?
Yeah.
Okay. So, let big M and little m be the max and the min of our image, respectively. We got that from our previous theorem, the extreme value theorem.
Yep.
Yep. Then, by the intermediate value theorem, for any y between little m and big M, there must exist x in our domain, our closed interval AB, such that f of x is equal to that y.
Yes.
Make sense?
Yeah, I see it.
That gives us that our image is an interval. It contains extreme points, and it contains every value in between those extreme points, so it's a closed bounded interval.
Mm-hmm.
Understand the proof?
Mm-hmm.
Wonderful. Okay. This next one, we don't really need to do. We've covered the rest of the main stuff. I guess I can let you guys decide whether or not you want to cover it. It would be our last proof. Do you remember how we talked about the distance between sets? No, we actually had a definition for the distance between sets. Oh, geez, I did not bring that up. Oh, well, might shake some. So, intuitively, if you're looking at this line and this circle, this open set, so it contains all the points inside. So the circle doesn't actually intersect that line. They don't actually touch. But what's the distance between those two sets?
0.
0. Same as if we actually filled in that point, then it still would have been 0, right?
Yeah.
Now, if I give you an open set here and an open set here, and I tell you that this distance from this point to this point is 1, what's the distance between those two? 1, right? You expect the distance to be the distance between the closest points, not a point here and a point here.
Yeah.
Okay, so the distance between the two sets was the greatest lower bound of all the distances between them. So look at all the possible distances, pick 2 points, find its distance, pick 2 points, find its distance, pick 2 points, find its distance.
So it's like the smallest distance between them.
Almost. Because if we do all those distances, then that could give us all the numbers between 1 and 3, not including 1. What do we want the distance to be? 1. So it's the infimum. It's the greatest lower bound we can find.
That makes sense.
Okay. So what we're doing here now is, sorry about all the markers changing colors. They were all terrible. It took me a while to find one that worked. Anyways, so what our last one is that showing, let xd be a metric space and let a be a subset of x. Then if we define this function f from x to r by f sub a of x to r by f of sub a of x, I'm now going to just say f instead of f sub a, but it's just to help keep in your mind that we're talking about with respect to set a, gives us a distance from that point to the set. So f of x gives us a distance from the set A to our point x.
Okay.
You with me?
Mm-hmm.
So A is some set that's already defined, and now we're defining a function with respect to that already defined set. So A is a constant set, that's given to us. Now we create this function using A. What does it do? It gives us the distance from any point you pick to that set A. If you happen to pick a point in the set, then that distance is 0.
What do you mean A is constant?
A is just some set. The point is that A isn't changing as we're talking about this. For some given set A, not for any set A. With me?
Yeah.
Okay, so this last proof is just showing that that function is continuous. That's the last proof. It's a lemma because you use this for later sections in the book, but we're not going to do anything with it. Did you want to go over this proof or not?
Let's go over it.
Let's go over it? Okay. So before we go over it, I wanted to remind you about a proof we did way back in chapter 4, I think. It's a way that we can show functions are continuous. This is the theorem that we're going to use to show it's continuous. So let's go over what this says. So if f is a function from x to y that's a function f from x to y is continuous if and only if for every element in the domain and for every open set containing its image, there exists an open set in the domain containing little x where the image of u is a subset of v. That is a lot of going back and forth between, so let's draw a picture really quick of our spaces that we're talking about. So here's big X over here, here's big Y over here, and then F maps this way. There's F. We're saying that F is continuous if and only if, pick some little x over here, there's a little x. Here's f of little x, right here. We're saying that the function is continuous if and only if, for every open set you pick around f of x, this was our v, there exists an open set around x, call it u, such that f of u is a subset of v.
Yeah.
That's what we're saying. If that holds for each x, then notice that unioning up all the x's inside that go to this v will give us an open set that mapped completely into it.
Yeah.
So you might have some intuition for how this proof might go. So this is what we're going to show. So notice how I'm going to start. I'm going to start let little x in big X and let v be open in R where f sub a of x is in v. You see how that's setting up this picture right here? Okay, so what's my job now? My job now is to find this u that's an open set containing x, such that f of u is a subset of v, and we're done. So that's where I'm going from here. With me? Now, since f of x is in V, and V is an open set in what?
What?
Well, what?
In
R.
R.
So our topology over here is actually on R, not some arbitrary set Y. It's actually, we know exactly what it is. It's R with standard topology, right? So since f of x is in some open set, then it's also inside some open ball that's a subset of that open set, right?
Yes.
Mm-hmm.
So since f of x is inside V, then I can find some open ball around it that is still entirely in V,
Yeah.
because that would be one of its basis elements,
Mm-hmm.
right? So then there exists some radius such that the open ball centered at this point with that radius is a subset of V.
Yeah.
With me so far?
And you're just saying U is that ball?
No, U has to be over here, my ball's over here.
Yeah, but can't you just
My
say
ball is an open set in R. I need to find U, an open set in X,
That maps.
such that its image is a subset of my open ball, which is a subset of V. And we're done.
Okay.
So that's how I'll do it. And then here's the U I'll use. Let U equal the open ball. Using our metric now D, notice that X has a metric.
Okay.
Right.
So different metric now. Here we were obviously using the Euclidean metric because this was just in R, so standard topology, standard metric. Here it's some metric we don't have a clue about, but we let U be the set of, be the open ball centered at X with radius epsilon halves. And we're going to show that the image of this thing, the image of U, is a subset of this ball, is a subset of V, and we're done.
Yeah.
Okay.
And that's where we're going. And it's going to be just a lot of work with inequalities using the triangle inequality for metrics. So let U equal this, the open ball centered at X. So U, maybe draw it over here to help us keep track. So we're going to take an open ball around X with radius epsilon halves. Now, of course, we're just calling that an open ball. We don't really know if this looks circular. It could be using the taxi cab metric where it's squared, right?
Mm-hmm.
So that's just terminology. Don't rely too heavily on your picture. Anyways, so let U be the open ball centered at X with radius epsilon halves, and it means to show that f of U is a subset of V. Right? Okay. So how am I going to show that f of U is a subset of V? I'm going to pick a random element in U, call it Z, and show that f of Z is in V.
Okay.
Okay.
So I'm going to pick a Z in U, which means that f of Z is in f of U, and so that implies f of Z is in V. I'm trying to show that this set is a subset of this set.
Mm-hmm.
So I need to grab a random element out of there,
A random element.
a random one.
Okay.
I'm calling that random element f of Z.
So
I'm really grabbing a random element out of here, which gives me a random element in here.
So it's basically for all of the elements in
Yes,
U.
I'm showing that for anything you pick in here, it's also in here. So this is a subset of this.
Gotcha.
So I'm grabbing a random thing in there, f of Z, while grab its preimage Z. So grab Z, something in U, and show that f of Z is in V, and we're done. So that's where we're going to go now. So let Z be some random point in U, and now I'm trying to show that f of Z is in V, and we're done. So let Z be some point in U, and let little a be any point in big A, our set that we were given. Okay?
Okay.
And then notice that my distance from X to Z is less than epsilon halves. Because Z is an element in this ball, U.
Yeah, that's right.
Everything in here, what's all the points in here? It's all the points whose distance to X is less than epsilon halves. So keep this in mind because that's going to be important for all our inequalities. Okay, so then, and little a is just a random point in big A. Our point here is that the distance to little a is going to be less than or equal to our distance to big A. Our distance to a set is always less than or equal to our distance to a point in the set. So we're also going to be using that fact. So if I say here's x, and here's a, what's my distance from x to a? It's this distance, right? But my if we grab a random point little a in here, like that, then my distance from x to little a could have only gotten bigger. Or equal to. Yes.
Okay.
So we are grabbing a random little a from big A, and these inequalities are going to be true for any little a in big A that we choose.
Right.
Okay, that's how we're going to do this. Okay, so then the distance from some random point in big A to x plus the distance from x to z has to be less than or equal to the distance from some point in little a to z. Triangle inequality.
Yeah.
I can't do two distances and get faster than going just straight there.
Yeah.
So taking 2 steps to go there is always greater than or equal to just going there, right? Similarly, over here, and the distance from x to z plus the distance from z to a has to be greater than or equal to the distance from x to a. You follow me there? Just a triangle inequality again? Good? Okay, so now, notice what we're doing as we go from here to here. All we're doing now is saying, now instead of looking at the distance from a to x, replace it with the distance from, I should have said the distance from x to a. Here we have the distance from x to a. This is for any little a that we choose. So in the limit, you can think about it that way if you want, that's the same as the distance from x to big A. Since this works for any little a, then we're going to replace it with that, and we're still just fine. Okay? Because this was true for any little a in the set. Similarly, the distance from z to little a, we replace with the distance from z to big A. To the whole set. I probably could have started with this line, but I wanted you to think through it some to see where these numbers are coming from. Similarly, we're going to replace the distance from z to little a with the distance from z to the set, and the distance from x to little a with the distance from x to the set. So you go with this inequality and this inequality?
Yeah.
Okay, lastly, I know that the distance from x to z is less than epsilon halves, right?
Mm-hmm.
So if I replace this with epsilon halves, we could have only made our number bigger. So if f of x plus this distance is greater than or equal to f of z, if I replace this with epsilon halves, it's still true for sure, because that makes this bigger.
Yes.
Okay.
So that is where this half of this inequality comes from, right here. You see it?
Mm-hmm.
And then similarly, oh, I had one more line to show you the subtraction. So going from here to here, I just subtract the distance from x to z from both sides. You see that?
Yeah.
And now, if f of z is greater than f of x when you subtract this distance, then it's still going to be greater when you subtract an even bigger distance. Right?
Mm-hmm.
So, when we can replace this with epsilon halves, in other words, and that gives me this half of the inequality.
Yeah.
Okay, I see your algebra.
Okay, what did we say? We just barely said that f of z is within epsilon halves of f of x.
Yeah, you did.
Yeah, we did. So if it's within epsilon halves of f of x, then it's definitely within epsilon of f of x.
Yeah.
Mm-hmm.
Right? So since it's within epsilon halves, then we know that f of z is within epsilon of f of x. So f of z is in this open ball. That open ball was a subset of v. So we show that f of u is a subset of v, and f of a is continuous. You see how I finish off?
Yeah.
Okay, so that is our last proof for the class. One thing I was going to do for you, if we had time, which we kind of do, is to show you now how you can now wrap your head around a definition of something clear at the end of the book called a manifold. Because somewhere down the road, I will continue from this class going into manifolds and starting a manifolds class. So, I want to introduce you briefly to manifolds because it'll probably be you guys that I'm doing this with. So, definition. Maybe specify really quick what a manifold is. A manifold, how many of you have heard the name Einstein before? Yeah, you've heard that once or twice. Did anyone know what he's famous for?
E equals MC squared.
That's true. But he has a theory out there with a very popular name.
Quantum, I forgot.
No, he's not quantum mechanics, so all modern physics is pretty much split up into the standard model, which is where quantum mechanics is, and the other half,
General relativity?
general relativity. That's what he does. So general relativity pretty much explains everything that happens in our universe on a large scale, and the standard model, which has quantum mechanics, pretty much describes everything in our universe that happens on a small scale. So between the two, we have a complete description of our universe. Now, we know our theories aren't perfect for sure because the two theories run contrary to each other. They make opposite predictions. And right now, there's no reason to pick one theory over the other. They can both be false, but they can't both be true. That's for sure.
Okay.
And they've both been extremely well tested, and they keep landing within they keep making perfect predictions to the extent that we can measure. So the margin of error is always within however delicate our instruments are. As we get more and more delicate instruments, we prove them more and more correct. It's crazy. Chances are both of them are going to need tweaking. Huh?
Yet they contradict each other.
Yeah, they're contrary to each other. Not contradiction. They're contrary. So, general relativity, which explains the geometry, it basically describes the geometry of our entire universe and how energy and matter affect the geometry. It describes gravity in terms of geometry. It basically is able to describe gravity perfectly, and then Serum describes the other three forces, which are electromagnetic, weak nuclear, strong nuclear. But it describes those three forces. Only 4 forces in the universe, 4 forces responsible for all the physical interactions we see. And those are them. So general relativity does gravity. It describes gravity. It's the mathematical model that we use to describe gravitational effects. It does an amazing job of it. And it describes it in terms of geometry. It shows how matter warps the geometry around it. So it tells you how this marker is actually moving in a straight line the whole time it's in free fall. And it looked curved to you, but it was actually moving in a straight line. It was moving in a straight line in its geometry. And so, all gravity is actually explainable if you know how mass bends the geometry. The common intuition that someone gives is, when I roll a marble, if I'm not pushing it, it just travels in a straight line, right?
Mm-hmm.
Now, if you go stand on a trampoline, so that you're in the middle of the trampoline so it bends down, and you bend down and you start rolling a marble, it's going to start orbiting around you because of how you're bending the trampoline and changing the geometry of the trampoline by standing on it. So you standing on a trampoline changes its geometry, so that marble's still moving in a straight line. It's just now, because of how the geometry's bent, it travels in a circle. So, similar intuition for the Earth bends the geometry here, and so the moon traveling in a straight line looks like it's going in a circle. Or this traveling in a straight line looks like it's following a parabolic path. Anyways, the basic model of a spacetime, which is what you use to describe general relativity, is a manifold. It's a manifold with such and such and such and such and such properties. Now, none of the such and such and such properties are trivial, and no chance of me helping you even come close to wrapping your head around them. But you can now wrap your head around a manifold. Well, a manifold is, at least. So it's a manifold with tons more structure, but it's still just a manifold. So, let's wrap your head real quick around what a manifold is. So an n manifold, it can be multiple dimensional. One-dimensional manifold, two-dimensional manifold, three-dimensional manifold. We'll see some examples. An n manifold is a Hausdorff. You better know that one or I'm throwing a marker at you.
Yep, I know it.
Well, that's Hausdorff.
Means Hausdorff means you can create two.
For any 2 points you pick, they have their own neighborhoods.
Yep.
Hausdorff topological space X with a countable basis. Now that countable might throw you off for a second, but you know what a basis is, right? Basis for topology. Countable basis means it is either the same infinity as the integers or less. So it could be finite or it could be that special infinity that the naturals, the integers, and the rationals are.
Okay.
The first example that you come across something that isn't a countable set is the real numbers. You can't count the real numbers. You can't put them in some, you can't count with some pattern for listing out all the real numbers and eventually list them all out. That's one rough way of saying it. So with a countable basis, in other words, its basis is somehow homeomorphic with a subset of the integers. There's one way that you can think about it. With a countable basis such that for each little x in our topology, has a neighborhood that is homeomorphic to an open n ball. This n and this n are the same thing. And an n ball, we mean exactly what you think. If I say what's a 1 ball, it's just an open interval. What's a 2 ball? It's just an open circle in R2. What's a 3 ball? A sphere. Here's a 3 ball. An open 3 ball doesn't include its boundary, but all the points inside.
Okay.
So that's what it's saying. So let's look at 2 examples really. Here's the torus. Torus, we're just talking about its surface. The torus is a 2-dimensional manifold. One, we're talking about, think about the torus as a subset of R3. With me?
Yeah, I think so.
Surface of a donut in R3 that you're used to. You're holding a donut in your hand. Think about just its surface.
Yeah.
Okay, so first off, is that Hausdorff?
Yeah.
It should be.
Yeah, it is. With the real numbers, for any points you pick, I can always pick such a teeny open ball around both those. If you pick 2 random points in 3-dimensional space, I can always find an open sphere containing this one, an open sphere containing this one that don't intersect, right?
Yeah.
Yeah. So, it's a Hausdorff topological space with countable basis. We won't worry about that one. That one is not as intuitive right now. Such that each little x in big X has a neighborhood that is homeomorphic to the open M ball. So now think about the surface of a torus real quick. If I pick a small enough open set on that torus, imagine that you were a little ant on this torus, right? I can pick a small enough open set around that point such that it looks like a regular circle to you.
Yeah.
You see that?
Looks like a regular circle to you.
Okay, let's think about the sphere. Let's think about a sphere. Same thing. Should have started with this one. This is way better anyways. The sphere, a sphere is a 2-dimensional manifold. Look at you. Go out on the earth and can you draw a circle in the dirt?
Yeah.
Yeah. Now, if the earth was a perfect sphere and you were to look at that thing, it's not quite a perfect circle. It's got some arching to it.
Yeah.
But you see how you can make a map from that circle to the perfect circle and have it be homeomorphic, right? It's just a little bit of bending.
Yeah.
You can create a map that just straightens it out, in other words. That's real easy to do. We've done way crazier transformations than that and still have homeomorphic. So, that's what we mean. If you use a sufficiently small circle, then that is the case. If you use a sufficiently small open set, that's the case. You can get something small enough that it looks like a circle.
Okay.
That's what we're saying. Notice that if it gets too big, you run into a problem. What happens if you try making your circle as big as the whole surface of the earth?
And it's just.
It breaks down.
Yeah.
How do you do that? What do you mean? So I can't take the whole surface of the earth and show that's homeomorphic to a circle. In fact, we proved that they're not homeomorphic.
a small enough one, you can show them.
But if you don't try taking too big of a set, if you keep it small enough, then you can basically get as close to you want as a perfect circle. Or you can get something that looks close to a perfect circle and then create a homeomorphism to the perfect circle, right? Open circle. So we mean actually a disk without its border. So that's what I'm drawing here. For any point there, if you use a small enough patch of the torus, then it's going to be homeomorphic to just an open disk. Right? I could take that patch and create a homeomorphism from that patch to this, where this is a regular disk in R2.
Okay.
That's what we mean by a two-dimensional manifold. Let's look at a one-dimensional manifold for a second. Just a circle. A circle is a one-dimensional manifold. What does a one ball look like? Looks like just an open interval, right? And we already talked about how something like this is homeomorphic to just an open interval.
Yeah.
Right? Trivial. So here's a one-dimensional manifold. Notice that if this was what your universe looked like, and you were a being that lived here, you would think that your universe was one-dimensional. You can go forward, or you can go backwards. And that's the only way that you can travel, because you just exist on that circle. If you were a two-dimensional person on the surface of a sphere, then you would think that there's only two dimensions. Right? We almost maybe think about an ant because they're so small in one dimension that you kind of think about it that way. But if you were a two-dimensional being, so even though, notice that this torus, it takes 3 dimensions for us to capture the torus, you can still imagine a two-dimensional being who can only move inside this two-dimensional universe, just move around on the surface, and to them, it's just a two-dimensional place. You can go left, right, up, down. They have no notion of going into the torus or out of the torus like we do. They can just move on the surface of a torus.
Right.
So, a space-time is a 4-dimensional manifold. It's a special 4-dimensional manifold. Where us beings living on this 4-dimensional manifold can comprehend 4 dimensions. 3 of space, 1 of time.
Yeah.
And we can only comprehend 3 spatial dimensions. We can't even comprehend what we would look like to someone who could see in 4 dimensions. Same way that, imagine that you were a 2-dimensional being again, and let's draw Peter's bedroom. So Peter, he goes into his bedroom, so there he is, and then he shuts the door. And now he thinks no one can see him, right? Because someone out here, they can't see through the door, so they can't see Peter. We 3-dimensional beings have no problem seeing Peter. We see him just fine. And that would baffle Peter. The same way that you'd be baffled that a 4-dimensional being can see inside your lungs. Yeah. So it's a cool area of maths that you can kick off into to start getting deeper into gravity and general relativity. And I still have another book that we could go through, which we go through the end of this book real quick. The last chapter of this book is manifolds, and then we can continue with a special type of manifolds called smooth manifolds, because the spacetime is a smooth manifold with other properties. And I have a textbook that we could go through that does that, so we'd just be doing analysis of manifolds, and it builds from there. So, but that's something that you're going to want to do calculus for first, because you need intuition for smooth. Smooth is very much related to, you can create continuous curves on this thing. So, anyways, that's the end of topology. That's our last class.